Now that we have stated and proven Cauchy's theorem, let's realize some of its consequences. As has been noted earlier, Cauchy's theorem is one of the most fundamental and one of the most powerful theorems in complex analysis. We will do justice to this claim by proving some very beautiful and striking consequences, the first one among them being the Cauchy integral formula. Cauchy integral formula is a powerful theorem in itself, and many times it forms that tool for application of Cauchy's theorem to conclude various things about holomorphic functions. Let me first write down the statement and we'll discuss more. The Cauchy integral formula. Let omega be an open subset of the complex plane and let f be a function holomorphic on omega. Fix a point z0, fix z0 in omega, and let r positive be such that the disk, the closure of the disk of radius r around z0 is contained in omega. Suppose gamma is a closed curve in omega minus z0 such that gamma is homotopic as closed curves up to a reparameterization. Maybe I shouldn't bother writing this, but let me put it down anyway. Such that is homotopic to what? It's homotopic to the circle of radius r around z0, homotopic to gamma 1 in omega minus z0, where gamma 1 of t is equal to z0 plus r e to the power it for t in 0 to 2 pi. This is the circle of radius r around z0, and what we are demanding is that gamma is homotopic in omega minus z0 to this particular circle. Then the conclusion is that f at the point z0 is equal to 1 by 2 pi I times the integral over gamma f of z by z minus z0 dz. Okay, let's look at the statement once more. Cauchy's integral formula states the following. Suppose you have a curve gamma which is homotopic to the circle of radius r around z0, where z0 is an interior point and r is such that the disk of closure of the disk of radius r around z0 is contained in omega. Suppose this gamma is homotopic to the circle, then the value of f at the point z0, it can be concluded by how f behaves on the curve gamma. So at points not in gamma like z0, you will be able to conclude what f is at z0 based on what we know about the behavior of f at gamma, or rather f on gamma. This is the type of rigidity that was being referred to earlier. So this in some sense captures the global behavior of the holomorphic function on omega. It's not that we focus at a particular portion of omega and how f behaves there. The function f, when it is defined on omega, has a global nature. Let's prove this statement. The statement is to conclude that f of z can be realized as this integral. This integral is many times called the Cauchy integral formula. Alright, let's give a proof. Since our curve gamma is homotopic in omega minus z0 to the circle of radius r around z0, and f of z by z minus z naught is a function which is holomorphic on omega minus z naught. The integral of f of z by z minus z naught over gamma coincides with the integral of f of z by z minus z naught on the circle of radius r around z naught. Let me write that down. Since f of z by z minus z naught is holomorphic on omega minus z naught, should think about why I say that it is holomorphic on omega minus z naught. Since this function is holomorphic on omega minus z naught, and our hypothesis is that gamma is homotopic to gamma 1 as closed curves, I'll assume that it's a reparameterization such that the domain of definition is the same, and because the integral doesn't depend on the reparameterization, we can always go to any reparameterization and work with it. Since gamma is homotopic, where in gamma is homotopic to gamma 1 as closed curves in omega minus z naught, and our function is also holomorphic there by Cauchy's theorem, we have the integral of f of z by z minus z naught over gamma to be equal to the integral of f of z by z minus z naught over gamma 1. This is by the second statement in the statement of Cauchy's theorem, which we proved last week. That is good because we have effectively reduced this integral to an integral on the circle of radius r around z naught. Let's draw a picture to understand what we have done. Suppose this is our omega, and suppose we pick a point z0 and r be such that the disk of radius r, the closed disk of radius r around z naught is contained in our domain omega. We will focus our attention on a much smaller disk. Let's say this is a disk of radius epsilon around z naught, and let's now focus on the curve of radius epsilon around z naught, and notice that with a straight line homotopy, which will be like this. By going along these lines which originate from z0, you will be able to get hold of a straight line homotopy from the disk, the circle of radius r around z naught to the circle of radius epsilon around z naught. So let me write that down in dz0 r bar minus z naught. The circle gamma 2 of radius epsilon around z naught is homotopic as closed curves to the circle gamma 1, and hence again by Cauchy's theorem the integral of f of z by z minus z naught over gamma 1 is equal to, which is the same as the integral of f of z by z minus z naught over gamma. This is the same as the integral over gamma 2 of f of z by z minus z naught. Notice that on the in a neighborhood of the closure of the disk of radius r around z naught minus the point z naught, f of z by z minus z naught is again a holomorphic function. This is in fact a holomorphic function on omega minus z naught. Notice that the homotopy that we have described in d bar z0r minus z naught, that is also a homotopy in omega minus z naught. So one could conclude by applying Cauchy's theorem on omega minus z naught that the integral over gamma 1 is the same as the integral over gamma 2. So we have this by either of the domains that we would have at our disposal. Anyway, we can conclude that the integral, so this is basically the integral of f of z by z minus z naught over gamma. Since f is complex differentiable at the point z naught, we can bound the Newtonian quotients at z naught by nm, since it is complex differentiable at z naught for epsilon, there exists an epsilon prime such that for epsilon less than epsilon prime, the absolute value of f of z minus f of z naught by z minus z naught, this is bounded by some m and m positive, such that this bound exists for z on the circle of radius epsilon around z naught. And this bound can be used to estimate our integral above. So let's look at the integral of f of z minus f of z naught by z minus z naught over gamma. So this is gamma 2, which is the circle of radius epsilon around z naught. Let's consider its absolute value. This will be less than or equal to the absolute value of the integrand, which is f of z minus f of z naught by z minus z naught, which is bounded by m, and the arc length of gamma 2, which is going to be 2 pi epsilon. So this is a bound which we have because of the holomorphicity or complex differentiability of f at the point z naught. Now let's focus on what is there here. What is there inside the integral? This is just going to be the integral f of z by z minus z naught dz over gamma 2 minus the integral f of z naught by z minus z naught dz over gamma 2. This is the absolute value that we are interested in. Let us now look at each of the integrals inside the absolute value separately. Integral over gamma 2, let's look at the second quantity first, f of z naught by z minus z naught dz. What is that? F of z naught is a constant, so this is going to be f of z naught times the integral over gamma 2 dz by z minus z naught. Now this is an integral which will be very similar to the integral of 1 by z over the unit circle. You should sit down and write down the change of variable to see that this is 2 pi I times f of z naught. This is precisely what the second integral here is going to be. And the first one, by Cauchy's theorem, we know is already equal to the integral of f of z by z minus z naught over gamma. By substituting both, we have this is equal to the integral or the absolute value of f of z by z minus z naught over gamma minus 2 pi I f of z naught. This is less than or equal to 2 pi epsilon m. Now let's divide by the absolute value of 2 pi I, which is going to be 2 pi, to get 1 by 2 pi I integral over gamma f of z by z minus z naught minus the f of z naught f prime, the number f prime at z naught. This is less than or equal to epsilon times m. Now for all epsilon less than epsilon prime, this is satisfied. Now by looking at epsilon going to 0, we conclude that this absolute value is equal to 0. By considering epsilon going to 0, we have integral f of z by z minus z naught is equal to f of z naught And that's precisely what we had set out to prove over gamma. So notice that gamma was a curve which was considered homotopic to the circle of radius r around z0. One thing we should keep in mind that we have used the fact that f is holomorphic on various domains at various points of time. Even though we started off with f being holomorphic on omega, at places where it mattered, we have considered f of z by z minus z naught, which is holomorphic on omega minus z naught. The Cauchy's theorem here was applied to f of z by z minus z naught rather than to the function f of z itself. Yet again, Cauchy's theorem here was applied to the function f of z by z minus z naught rather than to the function f of z itself. And the Cauchy's theorem was applied on omega minus z naught, not on omega. So we had to pick the curve gamma, which is homotopic as closed curves up to a reparameterization to gamma 1 in omega minus z naught rather than in omega. So as noted in the beginning of the proof, Cauchy's integral formula many times forms that powerful tool with which we can conclude things about holomorphic functions using the Cauchy's theorem. One such consequence is that holomorphic functions are complex analytic. Let me define what complex analytic is. It's like in the case of the real setting, we say that a function f from omega to c is complex analytic if it has a local power series expansion. If given z0 in omega, there exists a disk dz0r contained in omega such that f of z is equal to summation an, or such that the power series summation an z minus z0 to the power n, this power series converges in the disk dz0r to the function f. And as one of the first consequences of the Cauchy integral formula, let us prove the very powerful theorem which states that a holomorphic function is complex analytic. Let f from omega to c be a holomorphic function on omega, and let z0 be a point in omega. Suppose dz0 r bar is contained in omega, the closure of the disk of radius r is contained in omega, then for every n in natural numbers, let a subscript n be equal to 1 by 2 pi I integral f of z by z minus z0 to the power n plus 1 dz over the curve gamma, where gamma is the circle of radius r around z0, where gamma of t is equal to z0 plus r e to the power I t for t in 0 to 2 pi. Suppose we have gamma to be the circle of radius r around z0, then define an to be in this manner, then the series, the power series summation an z minus z0 to the power n, this converges in dz0r, and it converges to none other than f of z itself. So this theorem tells us that you start off with any holomorphic function, locally we have a power series expansion. Not only do we have a power series expansion, we know explicitly what the coefficients of the power series expansion will. Let's give a proof of the statement. Being holomorphic, it's continuous on the circle of radius R around Z naught, and hence we can bound the function f on this circle. Since f is continuous on gamma, we call that gamma is just this curve Z0 plus R times e to the power it. There exists m positive such that the absolute value of f of z is less than or equal to m on gamma. And if you look at the absolute value of an, this is the absolute value of integral over gamma f of z by z minus z0 to the power n dz, which is less than or equal to the term inside. If you notice, absolute value of mod f of z by z minus z naught. Absolute value of z minus z naught is equal to r because z is on the circle of radius r. So this is certainly less than or equal to m by r to the power n. Oh, there is an n plus 1 here. N plus 1, if I have not put it here, it is n plus 1 in the theorem as well. So it is less than or equal to m by r to the power n plus 1 times the arc length, which is 2 pi r. And this tells us that the absolute value of an is less than or equal to 2 pi m into 1 by r to the power n. So this tells us that the limit of mod an to the power minus 1 by n is at least r. Hence, by the definition of the radius of convergence, summation an z minus z0 to the power n, this converges in at least the disk of radius r around z naught. So we have our candidate an summation an z minus z0 to the power n as an honest power series which converges in dz0r. Let's now see that it indeed converges to our function f of z. To do that, let's focus our attention on dz0r. Let w be some point in dz0r. Let's draw a picture. Suppose this is our point z0 and this is our circle of radius r. Let's pick some w here. This is z0 and let's look at a disk of radius epsilon around z0. Let gamma 2 be the curve, the circle, the curve gamma 2 of t equal to w plus epsilon e to the power it for t in 0 to 2 pi, where epsilon is such that the disk of radius epsilon closure around z naught is contained in dz0r. Then let's now focus on the domain d bar z0 minus w. In this domain, by looking at the straight line homotopy again, by looking at the rays which originate from the center and going along straight lines, we will be able to get hold of a homotopy from the disk of radius epsilon around w to the disk of radius r around z naught. So let me write that down. In d of z0 r bar minus w, we have, so notice that this is our gamma 2 and this is our gamma. Gamma 2 is homotopic. I have not written down the homotopy specifically in both the cases. They are quite straightforward. It's just the straight line homotopy. It's a good exercise for you to sit down and write down what the homotopy is. It's an exercise which will make you familiar with the notion as well. Write down what the homotopy explicitly is and notice that it is indeed a homotopy on d bar z0 r minus w. Gamma 2 is homotopic to gamma, and hence by the Cauchy integral formula, f of w is equal to the integral of f of z by z minus w dz over gamma, where gamma is now the circle of radius r around z0. Note that we have used the Cauchy integral formula to conclude that the integral of f of z by z minus w over gamma 2 is the same as the integral of f of z by z minus w over gamma, and that this is equal to f of w by the previous theorem that we proved. So that's what is written here. F of w is hence equal to the integral over gamma of f of z by z minus w. Let's now look at f of z by z minus w here, or rather let's look at 1 by z minus w. Consider 1 by z minus w. This is equal to 1 by introducing a w naught term, this is going to be 1 by z minus z naught into 1 minus w minus z naught by z minus z naught. Notice that we are looking at z coming from the disk of the circle of radius r around z0. So absolute value of z minus z0 is always equal to r, and we know that the absolute value of w minus z0 is less than 1, is less than r. So this entire quantity, this ratio is less than 1, and we can write the geometric power series expansion here to conclude 1 by z minus w is equal to 1 by z minus z naught times summation w minus z naught by z minus z naught to the power n, where n is equal to 0 to infinity. This is precisely the geometric series expansion that we have, and by plugging it in here, substituting in star, we have f of w, this is equal to 1 by 2 pi I times the integral f of z into summation, maybe the z and z naught can be pulled in, this is going to be w minus z naught to the power n by z minus z naught to the power n plus 1 dz over gamma. Let's now try to see whether we can interchange the integral and the summation. We have to justify that if we can do that, and in order to do that, let's consider f of z into w minus z naught to the power n by z minus z naught to the power n plus 1. If you look at the absolute value of this is less than or equal to, remember that f of z is coming from the circle of radius r around z0, and we have already put a bound for f on that circle. This is going to be less than or equal to m by z minus z0's absolute value is always going to be equal to r to the power n plus 1, the denominator, times the absolute value of w minus z0 to the power n. And w being from the disk of radius r, this number is going to be less than r. So hence we have this is less than or equal to m by r into rho to the power n, where 0 less than rho less than 1. And because this geometric series converges by Weierstrass M test, and by applying the fact that the integral of the uniform limit is the limit of the integrals, we have summation f of z, the integral of f of z by z minus z0 to the power n plus 1 into z minus into w minus z naught to the power n dz over gamma. This is equal to the sum of the integral of f of z by z minus z naught to the power n plus 1. And notice that the term w minus z naught to the power n does not have any number, any z featuring in it, and therefore this will just be a number of this type into w minus w naught, sorry, z naught to the power n. And by calling these numbers as an, we have, this is f of w, remember that f of w is exactly equal to summation an w minus z0 to the power n. And that's precisely what we were trying to prove. For w arbitrarily picked from dz0 r, we have just shown that the series summation an w minus z naught to the power n converges to f of w, and hence we have proved our result. So if you recall, when we were discussing many results in the previous weeks, especially when we were discussing harmonicity of real valued functions, we were constantly imposing the condition of continuously differentiable on holomorphic functions. Now we have justified that that's a redundant condition. In fact, we have proved a lot more. In its disk of convergence, we know that a power series is holomorphic. Not only is it holomorphic, its derivative is also holomorphic, and we know the explicit expression for the power series expansion of the derivative. And using the fact now that the holomorphic functions on omega are locally power series expansion, we can say that complex differentiability is a local property. We can say that locally we will be able to talk about its power series expansion, which is infinitely differentiable, whose derivative is also holomorphic. So let me write down the corollary which I just mentioned. Let me allow you to think on the statement more deeply. Let f from omega to c be holomorphic, then f prime is also holomorphic. And because it's complex analytic, let me give you one more corollary which says that holomorphic function is infinitely differentiable. Let f from omega to c be holomorphic, then as a function from a subset of R2 to R2, f is infinitely differentiable. All partial derivatives of every order exist, and hence it is infinitely differentiable. And at this point, at this juncture, let me point out that this is one of the major differences that we will be seeing for holomorphic functions from that of the corresponding differentiable functions in the real setting. If you recall, we do not have any result of this sort in real analysis. There are functions which are differentiable, which are not real analytic. In fact, there are functions which are smooth, which are not real analytic. That's not going to be the case in the case of holomorphic functions. The levels of rigidity that are associated to holomorphic functions ensures that the moment f is complex differentiable and holomorphic in a domain omega, its derivative, it's complex analytic. That means that locally it has a power series expansion. Its Taylor series converges, and that its derivative is also holomorphic. So this is one difference which makes, or which gives us very many beautiful results about holomorphic functions as compared to real differentiable functions, which we will be exploring more in the next few lectures.